Indeed, the slope of the diagram will continue at a constant value until we reach the external load point D. You can see the slope of this diagram is continuing until we reach the point D where the external load is applied. When we have this kind of external load, there is a abrupt change in the bending moment diagram slope. You got it? We saw similar effect when we studied the case of a beam with internal hinge. You will note that this effect is consistent with our known values of the support reactions. The bending moment at B is clockwise to resist the anti-clockwise moment caused by horizontal support reaction at A. Because of this horizontal support HA, it is causing the anti-clockwise moment. So the moment at B should resist at opposite so that it will maintain the equilibrium position. That's the horizontal. Because of the horizontal force, the balancing anti-clockwise moment so that B is clockwise. However, as we move from B towards C, if we move from B towards C, because of this vertical reaction VA, it is causing clockwise moment. This VA HA is causing anti-clockwise, VA is causing clockwise. Because of this horizontal HA, the moment at this point it will tend to remain constant, but this VA is trying to reduce it because VA is acting in the clockwise, HA is acting in the anti-clockwise. That's the reason it is coming down until we reach this point, this one. After, if we move this one, this will start adding anti-clockwise to the direction of HA, and VA also it's increasing it the level of distance, but W also it will be opposing. That's why it starts building up. The same thing we can take it from the other direction also. Actually, VA begins to have a moment effect in reverse direction as we move from B towards C until it reduces to 0 at hinge point C. The same reasoning may be applied to the right hand side portion of our frame from corners at E to the load point D. At D, of course, the bending moments from the left and right must come to the same value. We can therefore complete our bending moment diagram for the frame by drawing a straight line from the value at E to D. Actually, it is coming on stopping here. The same way from here to here it will join. So we can complete the bending moment diagram like this. We must now determine the form of deflected shape of the frames. We start by indicating with the letter T the sides of the member which will be in tension, and therefore on the outer side of the curvature. Okay. Now let us come here. Now we note that at support points A and F are restrained both horizontally and vertically. As they are hinged, the slopes of the members may change at these points. The corners at B and E may rotate and move horizontally but may not deflect vertically. Also, we observe that the hinge C may deflect vertically, but it will have the same horizontal displacement as that of B and E due to the assumed axial rigidity of the horizontal member BCD. However, members connected at the hinge can take different slopes on either side. Here, if you see the A and F, these are horizontally and vertically restrained, but slope is free, so it can rotate. And if you see this B and E, it can move horizontally but not the vertically, because vertical member stiffness is more, so it moves horizontally. But if you see the C, it can move vertically because of the load effect. Whatever the value of B it's moving and E is moving, C also moves that much because this member is axial rigidity is there. That's the reason it is moving like this. If you see the members connected at C, it can have this, it will have different slope. The slope is not going to be constant. It will have different slope. It will have different slope. Let us now look separately at each of these two halves. Let us first look separately at the two halves of the frame, the part A, B, C and part C, D, E, F. For the moment, we will assume that the corners B and E remains in their original positions vertically, just above vertically A and F. And bending of the left hand side ABC takes place with tension on outside. If you take only this part ABC, the bending takes place with outer surface in tension. It moves vertically downwards. Okay. We can expect that part of the frame to deflect, as we have seen the left hand side of the diagram. On the right hand side C, D, E, F, there is an equal bending on the vertical member. This vertical member is equally bending it, but at the low W it starts changing the tension rapidly, and then it goes to E, changes rapidly because it's a rigid joint. On the right hand portion CDF, there is a equal bending on the vertical member, but the outside tension changes rapidly to inside. This outside tension rapidly changes to inside tension before we reach like inside tension, because it's moving tension because of the load like this, it moves, it deflects like this. So outside, this is outside tension comes, but here inside tension it comes. You can see it here like this, it moves, right? So tension is outside, but because of this load effect, then it starts to change to tension inside. Then because of the rigid point, it starts taking tension on the outside. That's how it's behaving. It's deflecting. It continues to C. Okay, this side of the frame would deform as shown. What we particularly notice that the downward deflection of C on the left hand side is greater than the right hand side. However, our frame is of course in reality continuous at the point C, because at point C it is continuous. So both have to coincide. So to coincide that one, this point here, it has to come up. So this point, it moves, rotates like this. So the same amount, if we move like this, it goes up. The same way, if it moves this side, it comes down. So equal amount of rotation, it happens at A and F as shown in here. So these are the point at C, these two are compatibly meeting each other. However, our frame is of course reality in continuous, and the 2 points C had to be coincident since they are shared by the both left and right parts of the frame. This can be achieved if we allow the points B and E to move horizontally. B and E, this point is the E, this point is B. So E and B has to move horizontally, rotating left part of the ABC in the anti-clockwise direction about A, causing the C to rise and move to the left. The amount of rotation will be the same for each part of the frame, must be just sufficient to make the 2 points C coincident.